Okay, colligative properties. This is the reason why we had to learn about molality. If you've ever made ice cream in an ice cream maker, you have to add salt to the ice. I think, well, just do it with the ice. It will never freeze. The ice cream will never freeze. And the reason you add salt to the ice cream maker is by adding salt, the ice gets colder. Think about that. It's bizarre, right? You got ice cubes, you put salt on them and they get colder? They do. And we're going to demonstrate this when we make ice cream in lab.
Does that alter the taste of the ice cream?
Well, yeah, if the salt got into the ice cream mixture, it would alter the taste of the ice cream. And that's why you separate the ice cream from the ice and the salt. It's important. So you can use salt to lower the temperature of the ice to about minus 10 degrees Celsius. This is because it lowers the freezing point of the water. And it's called freezing point depression because it depresses the freezing point. It's a colligative property. Colligative properties, there's several of them, are properties that depend on the number of particles, not on what the particles are. Doesn't matter what particle it is, just how many particles are there. And here we have to look at electrolytes and non-electrolytes a little bit differently because an electrolyte will separate into ions. And so if you have one formula unit of sodium chloride, you get 2 particles when it dissolves. Whereas if you have one molecule of sugar, and that dissolves in water, you only have 1 particle.
So is there something we can put ice water colder than just salt?
You could put anything in the ice water and make it colder. But then you're going to taste it.
Yeah, but is there something other than salt that would drop the temperature?
Even more. Something that's more soluble than salt, because you are limited by the solubility. The more concentrated that other substance is, the more it's going to depress the freezing point. It's a good question. So freezing point depression is a colligative property. Vapor pressure lowering is a colligative property. So here we've got pictures. So we've talked about vapor pressure, this dynamic equilibrium between a liquid and the gas. So here we have a closed container, and we've got water here, and the water is evaporating. It gets into the gas state. It can't go anywhere. It bumps around and eventually comes back into the liquid. So we have a constant pressure of water here, and that's called the vapor pressure. Now, if we put something in the water, if we put some other particles in the water, here we've got red particles, maybe it's sugar or salt or something, those red particles are getting in the way. They're blocking some of the surface of the water. So fewer of these water molecules can evaporate. To evaporate, the molecule has to have enough energy and be headed in the right direction to break through the surface, right? If there's other molecules here at the surface, they're going to get in the way. And those molecules will just get bounced back. So essentially this is reducing the surface area by occupying it with other molecules. So the rate of evaporation is diminished. If the rate of evaporation is diminished, then as condensation occurs, this concentration is going to get smaller until you get a new equilibrium. The new equilibrium has fewer gas molecules, and so the vapor pressure is lower. So you put something in the liquid, the vapor pressure is lowered. So that explanation is relatively easy to understand. A better explanation has to do with entropy. And this is a really crazy thing that happens. So here we have, it looks like a cake plate, right? We've got 2 beakers. One has pure water in it. The other has water with something in it. Let's say it's salt. So you've got a beaker of salt water and a beaker of pure water. So leave it there. It might take a while, could be days or weeks for this to happen. But if you wait long enough, the level of solution in the saltwater beaker will go up and the level of solvent in the pure solvent beaker goes down. So that's like magic, right? There's nobody coming in at night and moving water. There's no tube. There's no tricks. It's like it's going through thin air. Because it is going through thin air. Well, what's going on here? Well, the water is evaporating. The water evaporates from the pure solvent. The water evaporates from the solution as well. But in the solution, there is other things that is restricting the evaporation. So this has a lower vapor pressure. These gas particles now can escape from the beaker. They can bounce all over inside this cake plate, and some of them are going to collide into the solution here, the one with the salt in it. They're going to have a harder time getting out of here, and so they're going to get trapped. We know this nature's tendency towards mixing, called entropy, occurs in a single beaker. If you had salt water on one side and fresh water on the other side, they're going to mix spontaneously. This also happens when those two solutions are not in the same container. Is that crazy? Yeah.
Is it just the random movement of the particles that switches it over, or is there some attractive force?
It is random. If these were both both pure water, water in the gas state would still go back and forth. The molecules would be switching places, but the levels of water would stay the same. Here we see more water moving into this beaker, more water moving out of that beaker because of the solute. So the presence of a solute causes the vapor pressure to be lower. So of course we have an equation to quantify that. And it's called Raoults Law. And it quantifies the vapor pressure in terms of concentration. So the vapor pressure above the solution is equal to the mole fraction of the solvent times the vapor pressure of the pure solvent. When you talk about a mole fraction, you can talk about the solute or the solvent, right? Here we're talking about the solvent. The solvent is the one that's vaporizing, not the solute. So we're going to use the mole fraction of solvent. Vapor pressure of the pure solvent. If this is pure solvent, then the mole fraction would be 1. Right? And the vapor pressure would be equal to the pressure of the pure solvent. If this mole fraction was half, 0.5, 0.5 times the pure solvent vapor pressure, the vapor pressure will be cut in half. Vapor pressure is directly proportional to the amount of solvent in the solution. If you want to look at vapor pressure lowering, the change in the vapor pressure, this is derived from that. The change in the vapor pressure is equal to the mole fraction of the solute times the partial pressure of the pure solvent. So we can do problems like this. Calculate the vapor pressure at 25 degrees Celsius of a solution containing 55.3 grams of ethylene glycol and 285.2 grams of water. The vapor pressure of pure water at this temperature is 23.8 torr. So they're not asking for vapor point depression or change, they're just asking for the vapor pressure. So we'll just use Raoults Law. So the vapor pressure is equal to the mole fraction of solvent. What's the solvent here? Ethylene glycol or water? It's water. It's the one that there's more of, almost always. So this is H2O times the pure water vapor pressure. So this is the vapor pressure for pure water. We need chi water. We need the mole fraction of water. So the mole fraction of water is going to be moles of water divided by moles of water plus moles of ethylene glycol. I'm going to call it EG. Well, we've got masses, right? So we've got 282.5 grams of water, 285, just start over, 285.2 grams of water. So we'll convert that to moles. .285.2 divided by 18.02, 15.8268 moles of water. So we can plug that in here, 18.8268 moles divided by that plus something else. Ethylene glycol, that is in antifreeze, 55.3 grams. So we're given the formula there. There's 2, 4, 6 hydrogens, 6 times 1.008, plus 2 carbons, 2 times 12.01, plus 2 oxygens, 2 times 16, and then 62.068. So 55.3 divided by that, 0.89. 0.95 grams of EG, ethylene glycol. Yes, moles, thank you. There. 15.8268 divided by 15.8268 plus 0.89095. 0.947. Well, I'm not done yet, so I don't want to round that. 0.946. This is actually going to have 4 significant figures now. 46706. No unit because it's a fraction. So we're going to put that in here. 0.9467006 times the vapor pressure of pure water, 23.8 torr. 22.5.
Is that going to be the unit of pressure all the time?
Pardon me?
Is torr going to be the unit we use all the time?
That's a good question. Is torr going to be the unit for the pressure? It could be anything. millimeters of mercury, psi. Whatever this pressure is in, we're multiplying by a fraction which has no units. So then the vapor pressure of the solution will have the same unit. So you don't have to convert pressure units there. Any other questions? So sometimes the solution has a volatile solute in it, meaning the solute is also evaporating. And so then we have to look at the contribution of the solute to the vapor pressure. So we have ideal solutions and non-ideal solutions. An ideal solution is going to obey Raoults Law at all concentrations for both the solute and the solvent. And in this case then, the total pressure above that ideal solution is the partial pressure of the solute plus the partial pressure of the solvent. Non-ideal solutions do not follow Raoults Law, and that's because of interactions between the solute and the solvent molecules. If their attractions are strong, if they like each other, then the vapor pressure is going to be less. If they dislike each other, the vapor pressure is going to be larger. So here we have what happens with an ideal solution. We're looking at the mole fraction of A on the x-axis. And so starting with mole fraction of A being 0, and moving up to 1. And here we've got component B. When the mole fraction of A is 1, then the mole fraction of B is 0. So they're going opposite to each other. In an ideal solution, the vapor pressure of the solution is the sum of both of the vapor pressures at whatever temperature, whatever mole fraction. If you have strong solute-solvent interactions, they really like each other. That makes them not want to evaporate because they're like, I'm having a great time in this liquid. We're having a party here. We like each other. I don't want to leave. And so the pressures will be lowered. So there will be a bowing of this line for each of the components. And then when you add them together, you get a big dip in the middle. So at, roughly equal concentrations or mole fraction, 50-50, then the vapor pressure may be significantly less than you would expect. If the solute and the solvent have weak interactions, they don't like each other that much, then they're sort of motivated to leave faster than they would be otherwise. And so then the vapor pressures are higher. Any questions? Okay, this one's a bit of a bear. Okay, calculating the vapor pressure of a two-component solution. So here we have benzene and toluene. These are both volatile liquids. It's 25% benzene by mass, and we're given the vapor pressures of pure benzene and pure toluene. And we're asked to calculate the vapor pressure of each of the components in the mixture. So I'm going to call benzene B and toluene T. So if we look at benzene, the vapor pressure for benzene is going to equal the mole fraction of benzene times the vapor pressure of pure benzene. So we've got the vapor pressure of pure benzene right here, 94.2 torr. We need the mole fraction. Now they didn't give us like a mole fraction, they gave us a percent by mass. It's like, really? That's not very nice. So 25% benzene by mass, we have to convert that to a mole fraction. Well, what does it mean? 25% by mass mean 25 grams per 100 grams. So it's grams of benzene per 100 grams of the mixture. So that's going to be equal to 25 grams of benzene divided by the grams of benzene plus the grams of toluene. So that's 25 grams of benzene plus 75 grams of toluene. Because if I have 100 grams and it's 25% benzene, then the 75% must be the toluene. Okay? So to get the mole fraction, I need to find moles of benzene and total number of moles. So I need to convert moles of benzene, grams of benzene to moles. So I need the molar mass. They gave us the formulas there. 6 times the mass of carbon plus 6 times the mass of hydrogen. 78.11 grams per mole. So 25 divided by 78.11, 0.32006 moles of benzene. I've got 75 grams of toluene, so I have to convert that to moles. Got the formula for toluene, so 7 times 12.01 plus 8 times 1.008, 92.55. $75 divided by 92.55, 0.810. Moles of toluene. So the mole fraction then for benzene, it's going to be moles of benzene, 0.32006, divided by moles of benzene plus moles of toluene, I'm getting 0.283. Anybody else get that? So the mole fraction of benzene is 0.28313, and I'm going to multiply that by the vapor pressure of pure benzene, which is given as 94.2 torr. So that's going to be 26.67 torr. Then I'm supposed to calculate the vapor pressure of the toluene also. I'm going to make some space up here. So we got the same equation for the vapor pressure of toluene. Vapor pressure of toluene is equal to the mole fraction of toluene times the vapor pressure of pure toluene. We can just flip the mole fraction, yeah. We don't have to do this whole mess again. The mole fraction for benzene is this. There's only two components. The mole fraction of toluene is 1 minus that. So the mole fraction for toluene is equal to 1 minus the mole fraction of the other component. So 1 minus 0.28313, 0.71687. So the mole fraction of toluene is 0.71687, and the vapor pressure of pure toluene is 28.4 torr. .3 59 20.4 torr for the toluene. Any questions? This one's kind of a bear. Ready for part B? What's the total pressure above the solution? Well, just add them together, yep. So the total pressure is going to equal the partial pressure of benzene plus the partial pressure of the toluene. So I've got 26.670 plus 20.359 so 47.029 47 torr. Well, that wasn't so bad. But wait, there's more. The composition of the vapor in mass percent. Okay, so mass percent would be grams of benzene divided by 100 grams of the mixture, right? We've got vapor pressures. That's what we have to use to calculate the composition in the gas state. So we had the partial pressure of the toluene was 20.359 torr. I'm just going to write this down before it's gone from my calculator. And the partial pressure for the benzene was 26.670 torr. So a while back when we were talking about gases and partial pressures, we said that the partial pressure of a gas is equal to the mole fraction of that gas times the total pressure. So could we figure out what the mole fraction of benzene is in the gas? We know the partial pressure of benzene, and we know the total pressure, right? So let's just write the total pressure in here as well. So we just figured that out. That was 47.029. The fraction of particles that are benzene is equal to the ratio of the pressure from the benzene to the pressure of the whole thing. So the mole fraction of benzene is equal to the partial pressure of benzene divided by the total pressure. So that's going to give us 26.670 divided by 47.029. Calculator issues. .567. That's the mole fraction of benzene. Now the mole fraction of toluene then, because we have that, is easy, right? It's 1 minus that. So the mole fraction of toluene is 0.43290. So we got mole fraction. Now we need to get, in the first part we took percent and we went to mole fraction. Now we're taking mole fraction, we're going back to percent. Well, there's a couple ways to think about this. We could say, well, what if I had 1 mole of the mixture? That would tell me that this is the number of moles of toluene, this is the moles of benzene. I can use the molar masses and calculate the masses of the substances. That makes sense? So we're going to assume 1 mole of the mixture of the gas, the mixed gas. So then I have 0.43290 moles of benzene. So I have to convert that back, and that molar mass was 78.1 grams of benzene per mole. And I'm going to take the other mole fraction, 0.56709 moles of toluene. And I'm going to do that 92.55 grams per mole. Okay, 0.4329 times 78.11. 33.813 grams of benzene. 0.56209 times 92.55. 52.021 grams of toluene. So percent of benzene will equal the mass of the benzene divided by the total mass times 100. If it makes you feel any better, I'm finding this to be tedious as well. .4% benzene. And then thankfully the toluene is going to be easy. 100 minus that. 60.6% toluene. Yeah. Any questions? That's a bear of a problem. So vapor pressure lowering occurs at all temperatures. So the vapor pressure is directly proportional to the mole fraction. So if we look at this phase diagram, and we look at the liquid here, well, let's see, what's the best way to think about it? So the boiling point for the solvent is where its vapor pressure equals the atmospheric pressure. If the vapor pressure is lowered, if the vapor pressure is lowered, then you're going to have to get to a higher temperature before that solution boils. So that means it's going to boil at a higher temperature. We also see the freezing point depressing, or melting point. Melting point and freezing point, it just depends on which direction you're going. We also see that the melting point is depressed. So what happens is these move away from each other. I remember having a hard time remembering which one was elevated and which one was depressed. The boiling point and the freezing point move away from each other. So boiling point gets elevated, melting point gets depressed or lowered. We can calculate the change in the freezing point depression. It is related to the molality of the solution times a factor. The freezing point depression constant, that's going to be specific for the solvent and the solute, and you just look that up in a table. The change in the freezing point is actually a negative number, but for some reason everybody's decided to report it as a positive number. Because it's a freezing point depression, so the depression tells us the negative part, I guess. Here are the constants. Here we've got the freezing point depression, and we're going to see that the same equation works for boiling point, just using the boiling point elevation constant. So you would look those up. Calculate the freezing point of a 2.6 molal aqueous sucrose solution. This is a colligative property. The fact that it's sucrose doesn't matter. The concentration is what matters, and aqueous meaning it's got water as the solvent. So we look for water, and the freezing point depression constant is 1.86 degrees Celsius per molal. So 1.86 degrees Celsius per molal, and that's the freezing point depression constant for water. So the freezing point depression equals the molality times that constant. Molality is 2.6, handed to us, and 1.86. The molals cancel out. 1.86 times 2.6. 4.836 degrees Celsius, 2 sig figs. Is that the answer to the problem? No. It wants the freezing point. This is the freezing point depression. So the freezing point is 4.8 degrees lower than the normal freezing point. It's water, so we know the normal freezing point is 0. So 0 degrees Celsius minus the 4.836 is going to be minus 4.8 degrees Celsius. Yes?
So it's not pure water, though. It has sucrose.
Right. It's not pure water. If it were pure water, the temperature of the freezing point would be 0. The freezing point depression tells us how much the freezing point changes because we added the sucrose. So delta TF is the change in the freezing point. It doesn't give you the actual freezing point. It just tells you how much it changed. So you still have to know where it started from. And in the table, water, you should know the boiling point and freezing point. But for these other liquids, the freezing points and boiling points are given to you, because I would not expect you to know those. Boiling point elevation, same formula, just swap out F's for B's. So the change in the boiling point is the molality times the boiling point elevation constant. The reason we put antifreeze in the radiator of our cars instead of just water is that the antifreeze contains ethylene glycol or some similar substance that is non-volatile, and that causes the freezing point to be lower and the boiling point to be higher. So the boiling, you don't want your radiator boiling over, because intense pressure for one thing, and then the cap on the radiator is designed to let that out instead of having your car explode. So then you lose all your coolant. You also don't want it to freeze, because when water freezes, it expands, and that can crack your engine block. So antifreeze is good stuff. Calculate the boiling point. I'm not going to do this one because we're all tired. It's the same idea. Here you've got 3.6 molal. You look up the boiling point elevation constant. You multiply them. That's the change. You add it to the boiling point. Done. Osmotic pressure. Osmosis. Osmosis is the flow of solvent from a higher solution concentration, from a lower concentration to a higher. This is the process by which salt water causes dehydration. So I think of it this way, as nature's trying to make the concentrations the same. The semi-permeable membrane prevents the solute from going anywhere. So the only thing that can get through is the solvent. So to decrease the concentration, the solvent will move to the more concentrated side. The semi-permeable membrane allows some things to pass, but not others. Biological cells are contained by semi-permeable membranes. So we can look at an osmosis cell. So here we have a tube, and there's a semi-permeable membrane separating these two solutions. On one side we have pure water, on the other side we have, say, salt water. The water can get through the membrane, the solute particles cannot. So what will happen is the water will move to the more concentrated side. You could think of it in terms of trying to reduce the concentration. So we've got a net flow of water from this side to the other side. And that will cause the volume, the level of liquid on this side to go up and on this side to go down. Now nature's not too happy about that either. right? If there was no barrier in the middle, the levels of liquid on both sides would be the same. So there's a balance here. It doesn't like the concentration difference. It also doesn't like the level difference. So it'll go until it kind of gets a balance, because you have gravity pulling down here, right? The difference in the levels here represents a difference in pressure, and we call that the osmotic pressure. Another way to think of osmotic pressure is it's the amount of pressure you'd have to exert on this side of the tube to prevent the osmosis from happening. So we can think in terms of diluting the solution. We can also look at this in terms of an equilibrium. Sorry, my pointer's acting up again. There we go. So this membrane, water molecules can go through. If it was pure water on both sides, they would be flowing in both directions at the same rate. On this side, though, there are solute particles getting in the way, and so the rate of movement of water from the concentrated side to the pure side is less because the solute particles are in the way. On this side, water molecules can move that way because there's nothing blocking their way. And so we'll have a net flow of water to the left, to the more concentrated side. The real explanation, though, is entropy. Entropy is increasing by the spread of the energy. So osmotic pressure, the pressure required to stop the osmotic flow. That's capital Pi. Osmotic pressure is equal to the molarity times the gas constant times the temperature in kelvins. I will give you these equations on the next exam. So calculate the osmotic pressure in atmospheres of a solution containing 1.5 grams of ethylene glycol in 50 milliliters of solution. Okay, let's do this. Let's just say, I'm changing it. So we don't have to calculate the stupid molality. There, they gave us the molality. Oh wait, we don't want molality, we want molarity. Okay. .60 molar. I'm the teacher, I can make the question be anything I want, right? Osmotic pressure is equal to the molarity times the ideal gas constant times the temperature in kelvins. So the molarity, 1.60 moles per liter. We were supposed to calculate it, but we skipped that part. Times the gas constant, 0.08206 liters times atmospheres divided by moles times kelvins. And the temperature, 25 degrees, is 298 Kelvin. So here I've got moles and liters. There I've got molarity. So let's maybe write that out so it's a little clearer. Molarity is moles per liter. Moles cancel, liters cancel, kelvins cancel, left with atmospheres. So calculator went to sleep. 1.6 times 0.08206 times 298. 39.1 atmospheres. That's the pressure needed to keep osmosis from happening. Have you heard of reverse osmosis water filters? So in osmosis, you have the pure water diluting the salty water. Reverse osmosis, you're separating the pure water from the salty water or contaminated water. And you do that with pressure. So you have to put a great deal of pressure on the dirty water side to force the clean water through the semi-permeable membrane. That's what reverse osmosis is. Any questions about this problem?